One really simple way of ensuring communications integrity is using parity. Parity is essentially a really simple check that we can use to verify data integrity. For each byte of data that we have, we add an extra bit to it. Now we can actually do that on different size data types. It's not just necessarily a byte. You can have 6 bits or 7 bits of data, and you attach a parity bit to the end of it. And the parity is always 1 bit though. Now parity gives us 4 different cases. We can play with even parity, odd parity, mark, or space parity. Now essentially with even parity, what we want is the number of bits in total, all those bits plus the parity bit. We want there to be an even number of ones across all of those. With odd, we need to set our parity bit so we've got an odd number of ones across all of those. With mark, the parity bit's always 1. With space, the parity bit's always 0. So we're essentially both at the sender and receiver, we sum all the ones together, and we need to make it, when we're setting a parity bit, we need to make it even or odd or mark or space depending on which one we're doing. And we choose what we're going to assign as the parity bit accordingly from the sender. And at the receiver, we perform the same computation and check whether we've got the same as what we sent at the receiver, whether we're still got an even number or an odd number of ones. So this is something that needs to be agreed upon beforehand by both the sender and receiver. So for example, if you look at this, this data string here, we've got 5 ones that are present in that 8 bits or that 1 byte. If we're using even parity, we've got 5 ones, we need to add a 1 to it, and that will give us 6 ones. 6 is an even number. If we've got odd parity, 5 is perfect. So that's an odd number, we add a 0 to there, it makes it odd parity for us. Once again, the sender and the receiver both need to know what parity is being used at the onset. A few more examples there. If we've got all ones there, if we've got mark parity is always adding a 1, space parity is always adding a 0. Odd parity, well, we've got 8 ones, we need to make it 9 ones, so we add a 1 there, and so on and so forth for each of those different examples. Now, at the receiver end, it does the same parity count. If it doesn't match, it knows the data hasn't been received correctly. It knows that there's some error that's occurred somewhere on there. But there's some problems with parity. Now, firstly, and really significantly, it only detects odd numbers of bit errors. So if there's 1 bit that's in error, well, it's gone from odd to an even number. But if there's 2 bits in error, it flips both of them, and we've gone from an odd number to another odd number. And according to parity, there's nothing wrong there. Or we've gone from an even number to another even number, and it won't be detected by parity. Also, there's a really large data overhead here. For example, for every 8 bits or 1 byte, we've got 1 bit that's a parity bit. That's 11.1% overhead to just do this checking to make sure that we haven't corrupted our data anyway. Also, if we have a line that's pulled high or pulled low for a certain amount of time, it will pass consecutively even or odd parity because all those bits are high or all those bits are low for a particular time period. So some things to be aware of. Parity isn't foolproof, and there's some improvements that we can make upon it.